Okay, so good morning. So I will start by finishing the proof of the theorem that I stated last time. So let me recall the theorem. We are all on the same page. The theorem A. So the setting is the following. So you have G principal bundle. Endowed with a principal connection. And you assume that it has maximal Galois group. That is, that the Galois group of the connection equal to G. Okay, assume the Galois group of the connection is equal to G and that G is sparse. Okay. Okay, and then if you take, so let L be a leaf of the foliation and V an algebraic subvariety of P and denote by curly V an irreducible component of the intersection. Okay, so if the intersection is bigger than what you expect, okay, this is because something special happens, is that the projection of V intersected with L is included in a delta special subvariety. Okay, so if the intersection is too big, it means that the projection is included in a subvariety so that the Galois group is smaller. And so what we did last time is that we cleaned some of the easy cases. So the first thing is that we may assume that V is the Zariski closure of this curly V and that V is irreducible. And so in this, under this assumption, if we denote by V star the smooth locus of V, okay, so the foliation induced by delta, the foliation H delta, restricts the foliation H delta included in V star, okay, of rank the dimension of this curly V. Okay, and this foliation has a Zariski dense leaf, which is exactly this curly V. Okay. And so we said that we can assume that this is in 1 to dimension of y minus 1, otherwise we prove the statement. And so the goal is to describe what this foliation looks like to prove the theorem. And so what I was explaining last time is that, so to a principal connection, we can associate its connection form so its connection form will be a G-valued one form. So this is a form which goes from TP to G, the Lie algebra of G. Okay, which is determined by the following properties. The first thing is that this form, so I said that when you have a G-valued one form, you can view it as a tuple of one form. Okay, and this form defines the foliation. in the sense that if you look at the kernel of this form, this is exactly the foliation H delta. Okay. The second thing is that the integrability condition on nabla, not delta, is that the flatness condition of nabla, you can write it in this form, that this form satisfies the following equation. So I forget the one, so plus 1/2 of omega wedge omega is equal to 0, where this is a two-valued G-valued 2 form, and this is also a G-valued 2 form. Okay, and the last thing is that if you look at omega and you restrict it to the vertical vectors, this is the Maurer-Cartan form of the principal bundle. Okay, so let me explain what that means. So I explained before that if you're given an algebraic group, if you're given, so the example I gave last time, if you're given G, an algebraic group, okay, and you identify the Lie algebra of G to the tangent space at identity of G, you have a canonical G-valued 1 form on G, which is given as follows. You go from the tangent space of G to G, and if you take a vector at a point G, what you do is that you take the vector field and you pull it back by G for the action on the right. Okay, so you have a vector field at G, you use the isomorphism given by G to get a vector field on the tangent bundle. Okay, but this is so, but more generally, if P is a principal homogeneous space under the action of a group G under G, okay, and you fix, and we fix P, okay, and fix X in P. Okay, so when you look at the application which to P to G goes to P, which to G associate X and G, this is an isomorphism because P is a principal homogeneous space under the action of G, and you can take, you can define omega P, which is, so let's denote it phi X, which is phi X star of omega G. Okay. So as I define here, it looks like this depends on the point X you've chosen. Okay, but because the thing is right invariant and the action is on the right, okay, this doesn't depend, omega P does not depend on the point X. Okay, so every time you've got a principal homogeneous spaces under the action on an algebraic group, you have a natural G-valued 1 form on P. And so if you look at the principal bundle over X, the fibers, they are principal homogeneous spaces under the action of G. And so you get, okay, so on a principal bundle P from G, P to X, one gets a natural G-valued 1 form. Yeah. Natural omega, which goes from T of P over X. Okay, it's not defined everywhere. It's defined only on the horizontal thing. And you see that how do you do to complete it and get omega? You want that care of omega is H delta. So to get it from the connection, you go from TP to TP over X by modding out by H delta. Okay, and then you compose with this one and you get the big omega I wrote here. Okay. Okay, so now what is now I would go to the proof of the theorem. And the first thing I'm going to do is to use this assumption on the dimension. Okay. And so this is the first observation. Is that what tells you this assumption on the dimension? It tells you that for P in V generic, okay, so here in the smooth locus is enough, I guess, but I will only work generically on P. If you look at omega P of the tangent space of P of V, okay, this is a proper subspace of G. Okay, at every point, at every generic point of P, this is a proper subspace of G. And so why? So the dimension, so if you are in the smooth locus, the dimension is the dimension of V. Okay. At the dimension of the kernel, okay, of the restriction of omega to TV is equal to the rank of the foliation restricted to V is defined by the restriction of omega to V. So this, the kernel at a generic point, is exactly the same as rank, the rank of the foliation of H delta restricted to V star. And so this is the dimension of curly V. Okay, but this assumption here tells you that if you take the rank, so the dimension of V, the image as rank, which is strictly less than the int of G. Does that make sense? The image. Okay, so you see it's very easy to use this. Okay, and now comes the fundamental lemma of the proof, which says that this vector space does not depend on P. Okay. So the observation 2 is that there exists a Lie subalgebra H included in G, such that for all generic P, for all P in V, okay, the image, so omega P of T is equal to H. Okay. Here. Yeah. Okay, so how do you do that? So the proof of the second observation is the important part. So you write your omega you started with at omega 1 E1 plus omega k omega k ek, where E1 ek is the basis of T. Okay, and up to permitting the basis, we can assume that the first, so is it case, okay, about P. Okay, so we can assume that the first one are linearly independent over the field of function of V. So here I'm writing omega restricted to V. Okay. So I'm writing the restriction. So these are one forms on V. And I can assume that the first ones are linearly independent over C of V, and that the next ones, and omega of k plus I is equal to the sum of certain function in C of V for J is equal to 1 to K of the previous one. Okay, and showing that the image does not depend on P is the same thing as showing that the Bij are constant. Okay, is that clear? That at least for a generic P, because the image will be given by, so the image omega P of TPV will be given by so the dual basis of the EK of the EI is equal to Bij of P times the Ej star. Okay, for I is equal to 1 to 2. Okay. Does that make sense? Yeah. Oui. Yeah, you're right. For I equal to K from 1 to K minus to P minus K. Okay. So we want to prove that these functions are constant on V, but the foliation H restricted to V has a Zariski dense leaf. So we just want to prove that the Bij are first integral of this foliation. And so how we are going to do, let's take D, a vector in V tangent to of omega. And we are going to compute the Lie derivative with respect to this vector D of this one form. And this will be the same thing as computing the derivative. So this satisfies some kind of Leibniz rules. Okay. Okay. And so to compute this object here, we are going to use the formula that, so now if I want to compute this or this, the point is that they are all 0. Okay, so you can view it directly. So Lie D of omega I is equal to 0. So why is that the case? Because you can write Lie D as D times the contraction plus ID times the exterior derivative. And so if you compute Lie D of this object, if you contract by the vector field D, since D is in the kernel of omega, the contraction will be 0. Okay, so this part here will be 0. So when you apply the exterior derivative, you will still get 0. If you apply this part here, you want to compute. So okay. It's been too long. Right. So Lie D of omega I, this is D plus ID with the exterior derivative of omega I. So this part is clearly trivial. So it is equal to ID of D omega I. And now you use the integrability condition to say that this is what I wrote last time, a sum. ID is the contraction by the vector field D. Okay, this is for usually for one form, but it works for G-valued one form. Okay, this is the same computation. And so if you compute ED of D omega I said last time that the integrability condition tells you that you have coefficient in C times omega I wedge omega J, okay, and EK. Okay, but if you plug in ID in all of these, because we are in the kernel of omega, we get 0. So this is 0. And so you see that since this is 0, this is 0, this is 0, and therefore this is 0, and the Bij has to be constant. This implies that the sum from I is equal to 1 of k of the dBij omega I is equal to 0. They are linearly independent over C of V. So D of Bij is equal to 0. And so it implies that the Bij are rational integral of the foliation on V, but this foliation restricted to V doesn't have rational integrals. So the Bij are constant. Okay, the fact that H is a Lie algebra and not only a vector space also follow from the integrability condition. Okay, this is a very easy computation. And so this is now what we use, that G is sparse. And so since G is sparse, we can find a proper subgroup H of G such that my Lie algebra H is included in Lie of H. Okay. And now, so I have my bundle here, P over X. And what I can do is that takes the quotient of P by H. Project onto X. Okay, so there is an exercise about that. So we are going to use the exercise 2.1 in the exercise, which says that so you have your principal connection here. And because it's G equivariant, it descends to a connection here. So you have H delta. And here you have, how do you write it? Delta H. Delta descends to a connection here. Okay. Okay, so this is a general picture. And to say that the Galois group of delta is included in H is equivalent to say that delta H has a rational leaf. Okay, this is the exercise 2.1, if you want to. And so this is what we are going to use. So now we have our foliation H delta. So define L, which is a projection of G over H. Okay, and consider the foliation H delta plus on P defined by L omega, okay, by the composition of L and omega. So on P, you have two foliations. Okay, on P, you have the foliation associated to the connection, and so which has rank dimension of X. And now I just created another foliation H delta plus, which contains this one and which has rank dimension of X plus dimension of H. And what is the property of this foliation? By construction, V, or an open set of V, and an open set of V is contained in a leaf of H delta plus. Okay, by construction, this is how we created this foliation, that all the image of TPV are in H, and so when I modeled by H, they are all sent to 0. Okay. And so the point is that if I take these two foliations, I can project them in P over H. And see the observation tree, which is not hard, is that H delta and H delta plus have the same projection in P of P. So they have different rank, but actually, so this is somehow you project, so what is this foliation? Another way to define this foliation is that you get a foliation on P over H, and then you pull back this foliation. Okay. And so, but because V is included in the leaf of this one, so if I denote by rho, this implies that rho of V, okay, this implies that rho of V is included in the leaf of delta H. Okay. Okay, so this implies rho is the projection between P and P over H, that rho of V is included in the leaf nabla H. Okay, but as we said, that these leaves, they all have dimension, the dimension of X. Okay, so dimension of rho of V is less or equal to the dimension of X. And actually, dimension of rho of V is strictly less than the dimension of X. Why? Because if it was exactly dimension of X, this would mean that rho of V projects surjectively on X. Okay, so what does it mean? It means that delta H has a rational leaf. And so that gal of delta is included in H. But we assume at the beginning that gal of delta is equal to G. Okay. So the projection, so PH is a proper subvariety of X. So, okay, I could do the proof like that. I don't need to do it. Okay, maybe this you don't need, I mean, you can just do the proof with it. It's a subvariety of X. You don't need to know that it's proper. And if you look at gal of delta restricted to H, this one, okay, gal of delta H restricted to Y admits a rational leaf. Okay, and this rational leaf is just rho of V. Nabla H restricted to Y. Yeah, you want to gal. Oh, yeah. Okay, which implies that the Galois group of delta restricted to H is a proper subgroup. Okay, so here is how the proof goes. And so the main point is really to show that it doesn't depend on P. And then this is a standard construction. Okay, do you have questions about the proof? Okay, so now I want to give some applications. This principle to prove an Ax-Schaunel theorem for the J function and for other functions satisfying similar differential algebraic properties as the J function. Okay, and I need to define what are these similar differential algebraic properties. And so I will just give you some definition about rational projective structures. On P1. Okay. So let me first start by saying which differential equation the J function satisfies. So the J function satisfies an equation of order 3. So I'm going to write it explicitly. So this is y second over y prime prime minus 1/2 of y second over y prime square plus a certain function r of y prime square, r of y is equal to 0, where r of y is an explicit function. So it's y squared minus 1968y plus 2,654,208 divided by 2y squared. So I first want to give an interpretation for this function. And for this, I will use the Schwarzian operator derivative, which has lots of nice properties to explain the property of this equation. So I'm defining S of y to be the first part of the equation. So y is double prime divided by y prime prime minus 1/2 of y prime over y double prime over y prime square. So using the Schwarzian chain rule, Schwarzian chain rule, which explain how to compute the Schwarzian of a composition. So this is S of the composition of f and g. This is g prime square like that. So you can check that that a local inverse of a solution of this thing, a local inverse of a solution, okay, satisfies another equation. So this is satisfies. So local inverse. So I'm going to write it z is equal to z of y, satisfies an equation of this form. If you take the Schwarzian of z, this is just a rational function of y. So here, this is a Schwarzian computed for the derivation d over dy. Okay, so if you take a local inverse of this function, you will satisfy an equation of this form, which says that z satisfies an equation where the Schwarzian is a rational function of y. And so let me use another property of the Schwarzian. Okay, so let me call this equation G star. And so if Z1 and Z2 are two solutions of G star, then they exactly have the same Schwarzian. Then S d over dy of Z1 is equal to S d over dy of Z2, because the Schwarzian is a function of y. Okay, and this implies, by the property of the Schwarzian, that Z1 is equal to AZ2 plus B over divided by CZ2 plus Z for some matrix A, B, C, D in PSL2 of C. And so the local solution of G star define the projective structure on P1. Local solution of G star. Defined projective structure. Okay, an atlas of transition function are projective function on P1, where I get rid of the singularities on P1. We vote, so let's say on C, we vote the poles of the function. Okay, so this is how you can interpret this equation. That actually you look at the equation for the inverse function, and the equation for the inverse function are a projective structure. Okay, the solutions are the solution of this equation define a projective structure, and the function j is the local inverse of this function. So let me give a definition for that. Time. So first definition. Okay, then I will give you a more abstract definition if I have time afterwards. Okay, but I will work with this concrete definition. So a rational projective structure on P1 is a pair of equations so the first one will tell you that the Schwarzian with respect to z of y is equal plus y prime squared r of y is equal to 0. So this should be a plus and equal to 0. And the second one, so this equation, I will call it EC, EY. And the second equation is the equation of the other form, S d over dy of z plus r of y is equal to 0. Okay, these are the equations for the function for the inverse function. Okay, and the two equations determine each other. So you could pick one, but I didn't want to break the symmetry, so I pick the two. Okay, and what I explained just here is that the local solutions of EC define a projective structure outside of the poles of R of Y. Okay. And this is the equation for the inverse function. Okay, so let me make sense of that in a more abstract form. And explain how it relates to what we've been doing to the previous theorem. And so this is the construction one. Okay, so here I have the construction two. Here, it's here. And so to EC, to the equation, so I have the equation EC to EC, we can associate a PSL2 of C principal bundle over Y which is CP1 without the poles of R, endowed with a principal connection. And so here is a source of example for the object I've been describing, which is of this form. So I'm writing it as a construction because I will give you exactly the construction, but not its properties exactly. Okay, so you said Z equal to CP1. And we will think about Y with coordinate Y and Z with coordinate Y. Okay, and you denote by GK star of Z of Y the algebraic variety of jets of order K of locally invertible map from Z to Y. Okay, so as an algebraic variety, this is just, as an algebraic variety, this is a very simple object. No, okay, I took it in the wrong direction. That's why I have a note. Okay, because we want to do C. If we do Y, it will change. So we take the jet from locally from Y to Z. Okay. So this is so as an algebraic variety. It is the open set defined by z dot is not equal to 0 of so y times ak, so the affine space to the power k with coordinates. Y, z, z, second derivative of z, z. Here we think about these derivatives as formal variables. Okay, so this object is just the open set of the affine space with coordinate y, z, z, and everything defined by z dot is not equal to 0. Okay, and if you're given a map, analytic map from an open set of y to z, you can lift this analytic map to this J space. Then we get an analytic map from U to the set of terms, analytic and locally invertible. Okay, which to phi you associate to U, okay, to x you associate phi of x, d phi over d z at the point x, then 1 over 2 d phi over dz square. Okay, so let's forget the 1 over 2. And everything. Okay, so how do we make sense of this EC? So EC defines a closed algebraic variety of the third jet, okay, because you have an equation of order 3. Okay, and the following are equivalent. And phi is a solution of EC. The third J of phi, okay, just say, okay, is the solution belongs to C, takes values in C. Okay, and what we will use is the third possibility, is that if you take the second jet of phi, okay, it sends the vector d over dz, d over dy, sorry, to the vector d over dz plus, sorry, just don't want to, I'm always confused with which variable I should use. Z dot d over dz plus z double dot d over dz prime plus 3/2 of z over z dot square plus 2 of ry z dot d over d z dot. So you can ask why I'm making so many computations, okay? And it's because I started with a definition which is not formal, but a computation. So I did that to try to explain things a bit more easily, but you see that I have no choice than presenting things with a lot of computation, but I was trying to make things more concrete like that. Okay. And so you see that what this condition 3i tells you is that you have a connection on the second jet space of y over z such that the solutions of your equation are the section of this connection. Okay, so we have defined by H. Okay, the foliation generated by the vector field in tree I. Okay, and the main proposition is that this, so G2 star Y of Z project on Z on Y is a G principal bundle. Okay, and the foliation HC is a flat principal connection. And so how does that work? You have an action, so PSL2 of C, PSL2, G is PSL2 of C. So you have an action of PSL2 of C on Z. Okay, and from this, you will get an action of PSL2 of C on the jets of order 2, the jet of any order. Okay, so induce an action of PSL2 of C on DK star. But now this action here is sharply tree transitive. So if you think about an action which is sharply two transitive, what does that mean? It means you can take any 2 points to any 2 points. And so you can take any point on a vector to any point on a vector. And so the fact that this action is sharply tree transitive tells you that if I look at the two jets, okay, this is infinitesimal, this will be a principal action. Okay, and then this is the annoying thing. You can take this vector field that I wrote here and check that this is preserved by this action by PSL2 of C. Okay. Okay, so now let me give you the other side of the construction. So now, okay, so construction from Y now. We have an isomorphism. So now this is what I was doing with the chain rule. Okay, is that I was looking at the inverse function. And so I have an isomorphism between the jets from Y to Z and the jets from Z to Y, which is given by taking the inverse function. Okay, so in coordinates, you will send, okay, given by taking the inverse function. Okay. And so you see that this, so the fact that I defined the projective structure as these two equations, this isomorphism, I, will send the equation, EC on the equation EY. Okay. And we'll send, so we have, write it here. Okay. Okay, so denote by Y. Okay, the closed subset of GK star Y of YZ. So here I take YZ, yeah, so ZY given by the equation Y. Okay, then E of Y is equal to, okay. Okay. So this is the thing that we are having like before. So we have the conclusion. What kind of object we are going to work with is that we have P in Y a G principal connection, a G principal bundle. And those with a connection. But you see that using this isomorphism, so this P is G2 star of YZ. But using this isomorphism, I'm transforming G2 star of YZ to G2 star of ZY, and I'm projecting it on Y. And equipped with a second projection from P to Z. Okay. Okay, which is transverse to the foliation. Is that clear, this picture? This is a picture I will use next time. Okay, so you have, how do you think about the equation of the J function? Is that you have a principal bundle over a curve Y, one-dimensional principal bundle, I mean, equipped with a connection of rank 1, and you have a second fibration, which is transverse to the foliation, so that the J functions are actually the section of this one. Okay, so the equation satisfied by the J function is not directly a G principal bundle and those with a principal connection. But there is a second fibration such that this works. Does that make sense?
So you are in a threefold with three distinct one-dimensional foliations which are heterogeneous.
So this is 4. This is dimension 4. Okay. And I have 2 projections which are transverse to the same one-dimensional foliation. Okay. So now let me give the abstract version of this. Just want to give the formal definition that they give in the article. So formal definition. So let Y G be an algebraic group acting faithfully and transitively on Y. Okay. And on Z and Y, a smooth variety of dimension with dimension of Z equal to dimension of Y. Okay, so here is G, Y, Z. So definition, a rational G, Z structure on Y is a dy subvariety of this algebraic variety such that, so it's a dy subvariety C, such that on some open set U included in Y0, Y0 included, right? If I restrict C to Y0, is a G principal bundle. Okay. So you can just extract the structure I described here as a definition. Okay, and what you need is that you use, so this is, I was working with J of order K, but here this is a J of any order. Okay, and this is equipped with an action of the derivation on Y. And if you take a dy subvariety, this will restrict to an action on dy on this subvariety, and you will get a principal bundle with a principal connection. Okay. And so the goal of the next lecture will be to apply what the theorem A about transcendence to prove transcendence results about this kind of objects, but I will restrict to this kind of object that I have described here. Okay, now I will stop here today.
Any questions for me? No, that's fine. What about to break just a couple of information? So we will start the next lecture 15 minutes before, because we would like to here, information, because then we would like to take the because we would like to take the train at 1:30 to go for the hike. So we will start